All right, what'd you guys think? Open sourcing at its best, right? Our next speaker is from Microsoft. Marc Tremblay is a distinguished engineer in the Azure hardware at Microsoft. His current role involves defining and designing the silicon and the system roadmap for artificial intelligence and reducing the cloud tax in Azure. Throughout his career, he's demonstrated a passion for translating high-level applications requirements into optimization up and down the stack, all the way down to the silicon. Deep learning has been his focus for the past few years. He's the inventor of over 200 patents. Please join me in introducing Marc Tremblay.
All right. Thank you for the intro, and good morning, Amsterdam. Thank you for making me feel just like at home. The rain in Seattle is very similar to here. Now we'll start the technical part of the day. Quite a few slides. I'm going to take you on a journey from planetary scale data centers down to data centers, to rows, to racks, to chips. I'll share my views on AI, show you where that's going, the large AI workloads we run at Microsoft, and then I'll tie it all up together, describing the infrastructure we use, from Project Olympus, running CPUs, GPUs, FPGAs, and AI processors. And we'll see the kind of challenges we face running all of that. So let's start with the cloud, which at Microsoft is the Azure Cloud. Somehow we have to build infrastructure to run something that runs all these services, right? I'm just listing here Bing and Skype and Office 365 and add, LinkedIn and GitHub, and it's pretty amazing the volume that we have to serve on a daily basis. So to do that, we have data centers in over 140 countries. We have 54 regions, and this is part of the flavor of my European talks. I actually list the number of fiber we have in kilometers instead of miles. I was going to put a picture of the Ryder Cup, but decided not to do so at the last minute. And then, if we dive in, here's another European flavor slide, is the data center in Dublin. Gigantic installations, and multiply this by 54 regions, and it's just an incredible installation. Then we move in at the data center level. Think about this as a stamp of anywhere between 5 and 80 megawatts, hundreds of terabits per second coming in, partition into, imagine, 100 rows. Then you take these rows and you further divide them in racks. So we have about 300 kilowatts coming in. Divide that by 20 watts, you're at about 15 kilowatts per rack. The network is now 6.4 terabits per second, down to the rack, so that about 8 times 100 gigabit coming out of the TOR. And you go down to the server, you're about 625 watts and 100 gigabits per second, so totally oversubscribed on the TOR. These numbers can be easily off by a factor of 2. Depending on geography, depending how aggressive we are in some of our data centers, but I wanted to give you an order of magnitude. And by the way, we mostly publish these specs on OCP, so you can actually get the real values there. So down to the bread and butter, 2-socket, x86 server. Unfortunately, we have to produce all kinds of variations to support different workloads, from large database systems to large storage systems. And more we're dedicating silicon and servers to computing AI. So let's jump into what AI is at Microsoft. Today, you can go into Azure and run these services, in the field of vision, speech, language, knowledge, and Bing search, for example. And over the last few years, we've increased how well we do in AI. We, the industry, have taken the world from a perception standpoint, a comprehension standpoint, and we're getting closer and closer, if not surpassing, what is the so-called human parity. So I'm just sharing with you here some numbers where we've gone, and it's pretty astonishing. We have a long way to go, frankly. AI systems are still pretty dumb in some cases, but we're making incredible progress. And some of this comes from access to a tremendous amount of label data and, of course, incredible computing power. This did not exist in the late 80s when I was getting my PhD in computer science. We just didn't have that. And that's one of the reasons why we went through the AI winter. Now we have that, and it's really a renaissance of AI. Very exciting. Let's look at our large workloads. As a computer architect, we start the workloads and try to derive how we should build systems and chips. Well, you got Bing, Office 365, Cortana, our speech platform. And they all run frameworks like TensorFlow, PyTorch, and all this is migrating to Onyx, another open network, neural network interchange that we support heavily along with Facebook and AWS. Then you look at our thousands and thousands of Azure customers. It's a little bit harder to see what they run, but you can interpolate, and very similar frameworks, but usually much smaller workloads. This turns into pretty broad requirements for our AI computing. More specifically, neural networks are growing in size and complexity. I'll share with you some of these networks in the next few slides. And we often have to gang multiple neural networks serially and train them end to end. At Microsoft, we use many recurrent neural networks. We also use convolutional neural networks, but RNNs typically dominate. From very strict latency requirements, such as Bing, where batch size is 1, that means you have 1 query at the time that we run and spit out an answer, to large training jobs that take weeks and sometimes months, where we run very large batch sizes. So to conclude, we have an infinite appetite for speed and scalability. Our data scientists have no limits in terms of what they are asking us to produce. And for all the startups out there, I want to reemphasize how reliability and security are tremendously important, because these go in very robust data centers, and we just can't lower our standards there. So let's jump on a few neural networks I want to describe with you. And I thought I would introduce you to this kind of a nice animation on a classification problem. So we ran an experiment, and here we have the red dots on the outside and the blue dots on the inside. So that's our training set. And we're trying to derive a neural network that will process future dots on these pictures, and our neural network should be able to classify them into the red domain or the blue domain. So we're going to design this very simple, fully connected network. See the input layers on the left coming in basically as a position, and then we randomize the weights. You see everything is connected between neurons, and at the end we get how close we are to the blue, how close we are to the red as a probability distribution. So believe it or not, we're going to take these dots that I showed you, we're going to process them through this network in the forward pass, and we're going to go in the backward pass, adjust the weights. We're going to do this 50 times. That's the training part. And we'll get something like this. So initially, the neural network doesn't really know where the red dots are. So that's the red area. And look at the end. It really surrounds the blue with blue, which is what we want. Dots in the middle are kind of in between, and the red area is very isolated. So training reaches a very nice area at the end. Then the inference part would be us feeding it new dots, and it would tell us clearly if it should be in the outer region or in the inner region. And then we go from these simple neural networks to this neural network. And the odd thing about this one is, you see the connections are not symmetrical. They're all over the place, and they look kind of bizarre. And the reason is this was generated by another neural network, not by a human. So we're already using neural networks to build neural networks. No, that's not Skynet quite yet, but you know, we're using them for useful functions. And then in 2007 at Microsoft, we beat the world record for conversational speech. You see here, we were using a CNN for acoustic modeling, another CNN, then an RNN, LSTM, and so on. So all of a sudden, you have 4 or 5 networks in the series with hundreds of millions of parameters. So you can imagine the demand on main memory here. And that's how you get those error rates down to the few percents. We have other customers who come in and say, hey, I have a problem and I need a solution. Which neural network do I pick? A phenomenal challenge. So you can go brute force and do AutoML and use a ton of computers and blindly search for the best neural network model. Or, you know, we've been working on solutions that are much more clever into finding the right parameters and the right neural networks. Still requires a lot of computers, which we don't really mind. So how do we reconcile the cloud constraints or massive scales with these AI requirements is what I'm going to talk now. So we're always looking at the chip level for something that's faster, cheaper, that can provide us quantized leap. We want to train something that takes 22 days right now and do so over lunch. So our data scientists can actually have interactive research as opposed to pressing a button and waiting 22 days. And it's got to be, of course, easily deployable in our data centers. We don't want to bring super exotic cooling technology just now. And it's got to, you know, you can try to evaluate how well these chips and system will be at running networks that don't even exist. So I pay a lot of attention to that and look at the microarchitecture structure. So let's start with inference. Today, we use CPUs for a lot of inference. All the Cortana stuff is done in FPGAs, on CPUs. FPGAs, there's a track later on, an executive track where we spend a lot more time on this, but in Azure, in the Bing, we had strict requirements, and that's one of the reasons we use FPGAs. And we even use GPUs for image search. Online inference has strict requirements. You have a human on the other side, so we often use batch size 1. If it's just throughput and processing images on the side, we can use larger batch sizes. So on the training side, quite a bit different. You use the biggest, baddest GPUs, P40s, P100s, V100s, scale, you know, with scale-out systems. And I mentioned sometimes it takes weeks. I even ran into a job that took 2 months. It's just impossible to do research in this way. So, and large single domain reaching 100 petaflops would be great. And on the data type side, 16-bit floating point is working beautifully, and I'll show some slides on that. So it's not all about flops. In this chart, I'm showing the flops going from FP32 to FP16 basically increased by 35%, the horizontal blue line to the orange one. That's fine, but if you lose a little bit of accuracy, that may not translate directly into commensurate training time reduction. So that's those curves, and again, blue and orange. In this case, we saved some time, and this was run on NVIDIA card. I happened to have a meeting with the leader of that division on Friday, and that has improved tremendously. So we're still in an era that things are moving so fast, and now you kind of see a 2x improvement from going from FP32 to FP16 and sometimes more. So our choices literally is to pick for training and inference between all these technologies. Let's go first on CPUs. Well, we use millions of them in our data centers, and sometimes they're free. Hard to beat free, because we don't use them 24/7, 100% of the time, right? So we use them for inference. Our partners and our customers use them also. And the ISA is evolving nicely and rapidly from Intel, AMD, and the ARM ecosystem. I have a slide here that Intel shared with me. You can always tell it's an Intel slide from the fine print at the bottom. Lots of that. But I want to show the improvements going from 1x to 2.8x in a couple of years. That was just pure software. Going to 8-bit data types, 5.4x, going to AVX 512 plus new VNNI instructions, 11x. We're just talking about Moore's Law in the previous talk. Wow, this is a lot faster than Moore's Law. This is not like spec-int evolving at 10% per year. So we're going to see some tremendous improvements in the last few years. So don't dismiss CPUs because they're CPUs. For us, that's kind of the bar. Anything, you come in with a new accelerator, it better be 10x better price performance, right? And CPUs establish a pretty nice bar, and, given that there's security and there's virtualization and plethora of software that's available. Internally, we optimize the whole software stack. Here, we were at 107 milliseconds on this app, which was not shippable. And we just put an army of Microsoft software geniuses that shrank that by a factor of 20, just through software. All right, let's jump to GPUs. King of the Hill right now is large V100, 815 square millimeters, 300 watts, handles all kinds of data types, tensor cores, and proprietary interconnect. Very good machine. It's pricey and doesn't do so well on some of the neural networks, but currently the king of the hill. You stack 16 of them in the system. I'm not showing the heat sinks in this picture, fairly sizable, and you get this GGX2, $400,000 machine that currently is very hard to beat. At the inference level, NVIDIA just disclosed the T4. The picture is from them, the bullets, and from me. Actually, I think it's a quite nice machine running 1-bit, 4-bit, 8-bit components, 16-bit components. And they added virtualization. They added better tools to jack up the throughput for low batch sizes. So it's an interesting processor for inference on either in the data center or on the edge. Let's jump to AI processors. Wow, this is the wild, wild west. There's billions of dollars being invested here in Europe, in China, and in the United States. I've personally talked to 40 companies designing AI processors. They all address either inference or training. All of them rely on an intermediate graph representation and all running their own software stack. It's going to be wild. Not all of them will be successful, but the technology is pretty amazing, from optical computing, analog computing, and gigantic CMOS chips. Two categories are emerging: companies relying on fast external memory, and others try to leverage as much memory that's available on chip. Let me spend 2 slides on bandwidth, or 1 slide on bandwidth. So if you take the current state of the art, you have a 100 teraflop machine for basically 1 terabytes per second through 4 HBM2 stacks. So that's 1 byte per second for 100 flops, or 1 byte for 100 flop. In the old HPC days, the folks were asking us for 32 bytes per flop. So it's the other way around, right? The ratio is basically 3200x. We don't need that, so we're shrinking data types, we're exploiting locality, internal bypasses, we prune networks. Well, we're a long way from a factor of 3200. We need another factor of 25 to 50. New SerDes, more HBM2 stacks, HBM3 stacks coming out will give us an integer factor, but not a factor of 50. So the other approach is to try to locate most of the neural network, if not the entire neural network, on chip. And in today's technology, you can fit reasonable sized neural networks. I'm showing a bunch here that would fit in an on-chip memory that's totally doable in 16 nanometer and easily doable in 7 nanometer. So either technology requires a lot of power and systems to handle these high-power accelerators. So I'm going to share a couple with you here, and also there's an executive track later on discussing this, but here are 2 systems that we worked on with ZT. The first one is a couple of Intel sockets, and 12 P4s. I was just talking the T4s fall onto that. So, pretty nice box, dense box that accommodates all of that. The next one has a couple of AMD CPUs coupled with AMD GPUs. These are ZT systems that are at our booth as well. So, you start ganging these, plus the other system we described in the past where we can pile on, 8 cards at 300 watts a card. There's a, 4,000 watts. You put 8 of these in a system, all of a sudden you have 30 kilowatt racks. How do we deal with this? Well, fortunately, with Project Olympus, built in enough headroom to be able to provide enough powers and potentially cool these hotter racks. So AI in general, as different needs. Right now, we're renting VMs that are not really related to each other, and if they are, you can connect them somewhat loosely through the Tor. With AI and data parallelism, these processes need to be much closer in bandwidth and in latency. So that forces us to really design systems that are denser than what we were doing for general purpose computing. And therefore, the impact on mechanical and thermals for data center, for on-prem, for the cloud, and even on the heavy edge. Let me conclude. So certainly, hyperclouds provide the massive scaling, right? If we translate this into advances that I see out there for AI in hardware and software, I think we've got an easy factor of 100 in front of us, and I can kind of see the 1000x. Much better than Moore's Law. And the next few years are going to be quite phenomenal in terms of advances. I shared with you challenges we have with power distribution and cooling. We've got to find more exotic solutions in that space and discuss the impact on rack systems and data centers. To finish it all up, AI can do a lot of good. We have to be careful how we steer it, but the combination of incredible hardware, software stacks, incredible technologies, plus all the scientists working on this just point to a very, very bright future. Thank you very much.